Okay, and oh, let me make my pen thicker. Okay, so we are still continuing on in chapter 5 on probability. Okay, we left off on Monday, we left off with mutually exclusive events. Mutually exclusive meaning the probability of A and B happening together is what? If A and B are independent, if A and B are mutually exclusive, then the probability of A and B happening together is 0, right? If one happens, it makes the other impossible. Okay? So here we are going to talk about conditional probabilities. Okay? And we will write conditional probabilities something like this. This is the probability of A happening given, or if it is known that B has happened. Okay, so it's the probability of A happening given B has happened. Okay, so we will say, the probability, this is read as the probability of A given B. Okay, and so, here's an example of a conditional probability. We can say, let's imagine we are at the Chicago airport, so I don't know, O'Hare, Chicago airport in January. Okay, so we can say if there is a storm, the probability that the flight gets delayed is 0.7. Okay? And so that we're saying, the probability that the flight's delayed given or if there's a storm is 0.7. So we would write this as the probability of a delay, vertical bar, or given storm is equal to 0.7. Okay, so we're saying if there's a storm, we don't want to storm, but if there is a storm, then the probability that my flight gets delayed is going to be 0.7. Okay. On the other hand, if there is no storm, the probability of a delay is only 0.1. So our flight can still be delayed even if there is no storm, but the probability of delay is now only 10% or something. Okay, so we'll say probability of a delay given no storm is equal to 0.1. Okay, and there's nothing, these don't have to add up to anything or anything like that. Okay, so far so good. Okay, so probability of delay if there is a storm, or probability of a delay given storm, is 0.7. What is the probability of no delay given a storm? And over here I have probability of delay given storm. I'm sorry, given no storm. It's 0.1. Okay. So what's the probability? So if there is a storm, then the probability I get delayed is 0.7, which means if there is a storm, the probability I don't get delayed is 0.3, right? So the probability of A given B plus the probability of not A, or the complement of A given B, these have to add up to 1, okay? And likewise, these must also add up to 1, okay? But meanwhile, probability of A given B versus probability of, you know, A given not B, there's no relationship, okay? Okay, so A given B and A given not B, those could be entirely different things, okay? Okay. What if I flip this around? What is this asking? Well, how would we read this? This would be probability of storm, and we would say given, probability of storm given delay, okay? What does that mean? Okay, well, I don't have a number to put here, but conceptually this is the idea, okay? Let's say you have a friend who's going to catch a flight in Chicago, okay? And you're going to pick up your friend in New York or something, okay? You go to the airport and you look at the arrival screen, okay? And it says flight 321 delayed, okay? So you see that on the arrival screen. You say, oh, the flight's been delayed, and now you ask, oh, I wonder if they had a storm. I wonder if there was a storm, okay? So basically, you know, we see that the flight has been delayed. Okay, and now we wonder if there was a storm. Okay, and so here we are asking, you know, if we know the flight has been delayed, okay, so if we know there was a delay, what is the probability that there was a storm? Okay, and that is probability of storm given delay. Okay, and so if we see a whole bunch of delays for all the flights coming out of Chicago, then that would probably be a good indication that there was something going on. Okay, maybe not necessarily a storm. It could have been like, you know, some security threat or something. You know, it could have been a bunch of other things, but you know, it also it gives us a sense that, you know, something happened. Maybe there was a storm or something like that. Okay. Okay, and so it'll be very important that we can differentiate between delay given storm and storm given delay, or probability of A given B versus B given A. Okay, and again, A given B, and well, there is a relationship, so I won't talk about that just yet. Okay, so let's try something out here. Okay, let's say you surveyed a bunch of people. Did I flip this slide too quickly there? Are we okay? I did go back? Okay, all right. So you surveyed some people, and you asked, do you watch, I don't know, baseball on TV? Okay, and then so they can answer yes or no. And then, and the next question was, do you attend baseball games? If I can spell games. Okay, and again, yes or no. Okay. And so let's say we surveyed a bunch of people, and okay, and I'm just going to abbreviate this TV being baseball on TV versus no to the TV question. And then, and we'll say games versus no to the games question. Okay, and so, you know, I'm just making up some numbers here. So we'll say we surveyed 300 people, 90 of them watch baseball on TV, 210 don't. We'll say 60 of them attend games, which means 240 don't. And then I will say this, so that means 36, is that what I need here to add up? And 204? I hope I did this correctly. Okay. I'm thinking my numbers add up. They seem to add up, but I can make mistakes too. So, okay. So we can just start off here. Let me copy this for the future slides. Okay, so we can just start off with basic questions like, what is the probability that someone watches baseball on TV? And you would tell me the answer to that is, you can just call it out, or what is the fraction I would build here? 90 over 300, and we get 0.3, right? So 90 divided by 300, 0.3. Okay. And if I do probability of games, we would say this question is, or the answer to this would be 60 out of 300, 0.2. Okay. All right. So let me put up some answer choices here for our clicker question. All right. So we'll say 0.6, 0.9, 0.8, 0.3, 0.2, and then the question is, if we pick someone at random, what is the probability? What is dot dot dot? Okay, so we'll go ahead, fire that up. Shouldn't be too bad. And you can talk. You can talk to your neighbors. Okay, we'll say just 5 more seconds to get your clicks in. Okay, there. Now we'll say 5 more seconds. 5, 4, 3, 2, 1. Okay, do we have our clicks in? Yeah, okay, I'm going to hit stop. And that looks like the answer to me. 0.18. Okay, so the fraction we did here was we said, okay, well, how many people watch games and TV? 54 out of 300. 0.18. Simple enough, yeah? Did you guys make it harder than it needs to be? Okay, yeah. Well, that's life sometimes. What? Or was there concern here? Okay, so then, and so now, let's just let's do this, okay? And so now I'm going to say, so we'll say same answer choices. I forgot what they were. What was it? 0.6, 0.9, 0.18, 0.3, and 0.2, I think. Okay, so I'm going to say I pick someone at random. I pick a person at random. Okay, this person attends baseball games. Okay, what is the probability this person also watches baseball on TV? So I pick a person at random. This person attends baseball games. What's the probability this person also watches baseball on TV? All right, we'll just a few more seconds here. Get your clicks in. Okay, 5, 4, 3, 2, 1. Click, click, click. And that is correct. Answer choice B. Okay. And so what this is basically we are asking probability of TV given that the person watches or attends baseball games, okay? And so looking at the table, we are limiting ourselves to those who attend games, so our denominator is going to have 60. And out of those 60, 54 of them also watch baseball on TV. So our answer is going to be 54 out of 60, which turns into 0.9. Okay. All right. So I just want to quickly contrast these three similar but distinctly different quantities. Okay, so we have games and TV. Okay, which is always is the same as TV and games. Okay, so the order of the things inside the probability doesn't matter. And this is 54 out of 300 or 0.18. Okay? We have probability of TV given games, which we said is 54 out of 60 or 0.9. And then we would have probability of games given TV. And this is going to be 54 out of 90, which is 0.6. Okay, so these, they look similar, but they are also very different. Okay, so make sure we understand the difference between TV given games and games given TV. So one is asking, what's the probability that someone watches TV if we know this person watches games? Okay. You know, so if I ask, you know, what is the probability that, you know, a TV watcher goes to games, would your answer here be 0.6 or 0.9 or 0.18? So this one would be 0.6. Okay, this is probability that given a TV, so you know, we're asking what's the probability that a TV watcher goes to games. So the part that is known is the fact that this person watches TV. Okay, this is the quote known part, and this is the part that we are asking about. Okay, so again, make sure we understand these differences here. Questions? I have to say, I really like sitting here and seeing the class. You know, when I first started teaching, I used the blackboard, but it always felt so lonely because you're just facing the blackboard, and now I get to see all of your faces. Some of you are not paying attention, and that's okay. But most of you, many of you are smiling and looking at me. Makes me feel good. Okay. So, all right. So the general form is probability of A given B is going to be the probability of A and B divided by the probability of B. Okay? And likewise, the probability of B given A would be the probability of A and B divided by the probability of A. So the given part goes into our denominator, okay? And so, you know, with our baseball example, when we ask probability of games given TV, if we followed the formula, I think our thing ended up being what was it, 54 out of 90, and we said 0.6. We could have said probability of games given TV following the formula would be probability of games and TV divided by probability of TV. We said games and TV was 54 out of 300 divided by 90 out of 300. And this indeed simplifies also to 54 out of 90 or 0.6. Or, you know, if we turned it into decimal, it would have been 0.18 divided by 0.3. We would have also gotten 0.6. Okay, so however you do it, if you have the table, it might make sense to just go straight to the counts and divide them out, but that the table may not always be provided to you, and so you might have to figure out, you know, A and B divided by the probability of B, or something like that. Okay. We can also discuss independent events. Okay. So just want to make sure you guys have this all written down. Just want to make sure I'm not forgetting anything about this. Okay. Okay, so we also have independent events, okay? And we'll say if two events are independent, okay, that means the outcome of one event has no influence on the outcome of the other event. Okay, so two separate coin flips would be independent. So I'm sorry, let me just say examples of independent events. So two separate coin flips would be independent. So two separate coin flips are independent of each other. Okay, so the outcome of one coin flip would have no influence on the outcome of the other coin flip. Or, you know, dice rolls or coin flips and dice rolls, those are independent, okay? A coin flip and, you know, a die roll, also independent, okay? Those would be examples of independent events, okay? On the other hand, the storm and the flight delay is not independent. Okay, because when there is a storm, that influences the probability of a delay. Okay, so the presence of a storm, or the presence or absence of a storm, affects the probability of a delay. Okay, and it doesn't have to necessarily be a cause and effect type of thing. Okay, you can think of, so even so it'd be silly to think of that a flight delay has any influence over the weather. Okay, but it would still be correct to say that whether the flight has been delayed or not changes the probability that there was a storm. Okay, and it's not that the delay itself influences the presence of a storm, but it's just that, you know, if we look at the arrival board at the airport and we see all these flights being delayed, then we can kind of infer from that you know, maybe there was a storm or maybe there was something that's causing all these delays. Okay, so also, and vice versa, the presence of a delay, you know, kind of changes the likelihood that there was a storm. Likelihood or probability, likelihood that there was a storm. Okay, and it's not that one is causing the other. It's just when we're trying to come up with probabilities, we know that there's some kind of relation between these. Okay, and so, do we have all this written down? We're good? Okay, so if A and B are independent, then that means the outcome of A has no influence on B, and the outcome of B has no influence on A, right? So the outcomes of A and B have no influence on each other. Okay, so symbolically, what does that mean? The probability of A given B would equal what? What would the probability of A given B? This would just be the probability of A, okay? Because basically what we're saying is that knowing that B has happened or B didn't happen, this doesn't give us any more information. The probability of A happening is just the probability of A. It doesn't. We don't care if B has happened, or we don't care if B didn't happen. So the probability of A given not B would still be just the probability of A. Okay? And meanwhile, the probability of B given A would be equal to what? Probability of B, right? Okay, and so armed with this knowledge, we can now check to see if events are independent, okay? Are two events independent? Okay, well, we just check. Does probability of A given B equal probability of A? And if the answer is yes, they are independent. And if the answer is no, not independent. Simple as that. Okay. And so again, make sure you are checking probability of A given B. Is that equal to the probability of A? Okay, and don't mix this up and check probability of B given A or something like that, because those are unrelated or just different quantities. Okay, so let's try out an example here. Okay, so we'll do a silly example where we already know kind of the answer to this question. Okay, I'll say, is wearing glasses independent of being left-handed? Okay, and what is our answer? Yes, right? Okay, or at least, we have no reason to believe that being left-handed will either increase or decrease your chance of wearing glasses or vice versa, okay? It's not like, is wearing glasses independent of being a fighter pilot? No, okay? You won't qualify for to become a fighter pilot if you wear glasses, or at least for the U.S. Military, or is being left-handed independent of being a baseball pitcher? Also, no, there's a link there. But over here, glasses and being left-handed, we're not expecting any kind of relationship here. But I'm going to make up some numbers here to kind of illustrate how we can check to see if things are independent. So I'm going to pretend like I surveyed 105 people, and we will say, so here we're going to have left-handed versus not left-handed, and this will be glasses versus no glasses. Okay, What do I want to put here? Okay, so then we can say, to check for independence, mathematically. Right, because I could just as easily change these labels from left-handed and glasses to do people who blah blah blah, are they more likely to whatever, okay? So we can change these, and the news organizations are always trying to find little patterns about stuff. They say, like, this group of people are more or less likely to support this candidate, and so they say supporters of so and so are more likely to be young, and so supporters of so and so are more likely to be this look like this or something. So they're basically asking, is support for a certain candidate independent of some other factor, okay? And so here we're just asking, is someone who's left-handed more or less likely to wear glasses? We already know the answer to that is going to be that there's no relationship there. But here, to check for independence mathematically, what we're going to do is we're just going to say, is the probability of A given B, is this equal to the probability of A? Okay, this is all we're going to do. All right, so we just have to pick one of these to be A and one of these to be B. Okay, so perhaps just arbitrarily, I'm going to just say, okay, well, I'm going to say left is A. So I'm going to say, is left given glasses, is that equal to probability of being left-handed? Okay, all right, so what is the probability that someone is left-handed? Just if we select someone at random from the table. Our answer there would be 15 out of 105, and I would get 1 out of 7 over on this side, okay? Okay, and over here, what is the probability that someone is left-handed if this person wears glasses? We would say 7 out of 49, right? Okay, so if someone wears glasses, what's the probability this person is left-handed? 7 out of 49, and we get 1 out of 7. Okay, and so we get 1 out of 7. 1/7 is equal to 1/7. They are equal. Therefore, they are independent. Okay, now I have to kind of say, this works out because I made up these numbers and I purposely picked this, okay? Now, in a real-life survey, it could turn out that instead of getting 7 out of 49, we got 8 out of 49, or something like that, okay? 8 out of 49 people being, the probability of being left-handed given glasses if we just surveyed another group of people. And in that case, you would get 8 out of 49, which is ever so slightly different from 1/7. And at this point, we would just say, oh, some other number, something different from 1/7 isn't exactly the same as 1/7. And then so at this point, we would just say, okay, they are not independent, okay? But there's probably, something doesn't quite feel correct about that. And so later on in the course, we're going to do what we call the two-proportion test, where we're going to say, is the proportion 1/7 the same as the, is it different from the proportion 8 out of 49? And then, there's this term called statistically, or significantly different, okay? And we'll learn the math behind it, but later on, if you did a study and you got 8 out of 49 versus 15 out of 105, and you get something a little bit different from 1/7 versus 1/7, the math in that statistical step will say they are not exactly the same, but they are not significantly different, okay? And we'll learn about that later. Okay, but right now we're just going to go kind of with the strict rule: is 1/7 the exact same as 1/7? Yes or no? Okay, so if they're a little bit off at this point in the game, we're going to say then they're not independent. Okay. You know, again, this was, I just kind of picked left given glasses arbitrarily. I could have just as easily done probability of glasses given left. And here I would say, is this equal to what? Probability of glasses, right? Okay. And then so glasses given left would be 7 out of 15. Is this equal to 49 out of 105? Okay. And 49 out of 105 also simplifies to 7 out of 15, and we would say, yes, equal, so independent. Okay, and so, you know, if they're independent over, you know, whatever labels you, whatever you decide, whether you choose glasses given left or left given glasses, as long as you're doing the correct comparison, you know, glasses given left, is that equal to probability of glasses, or probability of left given glasses, is that equal to the probability of left, you'll come to the correct conclusion. Now, some common mistakes that students make are, you know, they will compare, is this fraction 1/7, is that equal to something else over here, okay? And if you do that, they're not going to be equal, okay? So you have to just make sure that you are doing the correct comparison of A given B, is that equal to the probability of A, okay? Because if you do the wrong one, it's not gonna work out. Okay, so take your understanding of independent events and your understanding of mutually exclusive events, and we will end with this one last clicker question, okay? And the question is, if two events, A and B, are independent, could they also be mutually exclusive? Okay, and your answer choices are yes or no. Okay, and you can talk about this. Yeah, I mean, what doesn't, probability of A is what, 0.2, probability of B is 0.5, it doesn't matter. Just some events, probabilities of A and B, if A and B are independent, could they also be mutually exclusive? So that's the question. Okay, so just a few more seconds, get your clicks in. 5, 4, 3, 2, 1, click, click, click. All right. Okay, let's see what you guys have said. And the answer, correct answer is B. Okay, so let's just discuss this, and then I'll let you guys go. All right, so listen up. Okay, so if two events are independent, then the outcome of one has no influence on the outcome of the other. Okay. On the other hand, if two events are mutually exclusive, okay, that means if one happens, it makes the other impossible, right? Because the probability of A and B would be equal to 0. Okay? And so if they are independent, they can't be mutually exclusive, because mutually exclusive means that one happening makes the other impossible. So the outcome of one does influence the other in the fact that the outcome of one will make the other outcome impossible. So if two events are independent, they can't be mutually exclusive, or if they're mutually exclusive, they certainly aren't independent. Okay, that's it. We'll see you guys on Friday for the exam. Good luck as you guys study.